So we're going to look at just one more algorithm for finding a minimum spanning tree. It's another greedy-like strategy, and it's called Prim's algorithm. What Prim's does is it builds a tree node by node. It starts with basically a tree that only has one node in it, and it keeps adding one extra node and one extra edge every time that it, on every iteration of this algorithm. So given that it has some current tree x, it's going to ask, what is the cheapest thing I can attach to x to increase the size of this tree by 1? And it looks at all of the nodes that are attached to x but aren't in x, and it says, which of those edges is this cheapest, has the lowest weight associated with it? And it takes that edge and it adds it, that node and that edge into x. It then checks, am I done? Have I completed this? Have I built out this tree to cover all of the original graph? If I haven't, then go back to step 2 and then just repeat this process. You're going to take the edge that is that's smallest, that attaches a new node into x, and you're going to incorporate that into this tree. And you just keep doing that process. Let's just look at it in practice. Let's say that the root node is a. So currently, x is just this node a here. We now look at the two nodes that attach that are connected to. So this is our x here. Right, x is currently just a. Now we're noticing that there are two nodes that attach into x. We have b and c, but notice that c is closer. C has an edge into x, which is just unit 1, has weight 1. So we're actually going to choose c now. Now x is a and c. Now we look at all of the things that attach to x, that attach to a and c. And we have B, we have D, and we have E. Which of the edges that attaches to X is the smallest? Well, I guess I have three options here. I could either use this edge right here, I can use this edge right here, or I can use this edge right here. Let's utilize this edge. So I'm now going to attach B using this weight 2 edge. And now I look at all of the nodes that are attached to x, but are not in x, but are the cheapest. What's the cheapest node I can attach to x? The cheapest node is going to be D. You'll notice that D has an edge weight 1 attachment to x. So I can now take D and incorporate it into my tree. Next, I look at the two remaining nodes that are attached to x that aren't in x. That's E and F. And I notice that I can attach, the cheapest one to attach is going to be node E. I can attach it using one of two different edges, but I'm going to use this edge right here. And finally, I only have one node left to attach. The cheapest edge is this one right here, so I incorporate that node and that edge into X. And now I'm done. I have a minimum spanning tree. The total weight of this spanning tree is 1 plus 3 plus 2 plus 1 plus 1, which is a total of 8. So I got a minimum spanning tree with value 8, and you can check that there isn't any better spanning tree than with weight 8. 8 is the optimal value you can achieve here. Great. So it's worth noting that Prim's algorithm is actually surprisingly similar to Dijkstra's algorithm. It may not have seemed like that at first glance, but actually the code I have here is almost identical. I had to change a couple of data structures and a couple of lines of code to produce something very similar. The key detail here, the reason why they're so similar, is that in both cases they have to maintain a cost data structure that tells you how cheap is it to incorporate any new additional point into my solution, and I should simply pick the cheapest cost item off of this data structure. And that data structure in both cases is actually a heap, a min heap. So we're actually using the same min heaped data structure as we were for Dijkstra's algorithm. This is called heap dict. It was from some code I got off the internet. So this MST edges is essentially my X from the previous slide. This is going to maintain all of the edges that I'm adding to my solution X. Initially it's empty. And what I do is I maintain these neighboring nodes heap data structure, which should incorporate all of the nodes which have not yet been attached to the solution, and it should store how close they are with one single edge jump. What is the cost of jumping into the solution X? And essentially, what this loop does is it pops off the closest item from the heap. It says what's the node that's closest to the current solution. That's what this pop item call is doing. It's taking this lowest priority item off of the heap. And now it's going to incorporate that closest edge into the final solution. What that how I should be attaching this new node to my solution, and then essentially it runs through all of the neighbors of this new node, and it just tries to update how close they are to this temporary solution, which is MST edges, or X. What was X on the previous slide? And it says if it's found, if the edge, the new edge would make it cheaper to jump into the solution, then we just need to update our heap data structure to change the priority value on each of these neighbors, on each of these items. So again, this is a very similar algorithm to Dijkstra's algorithm, and it's using a different data structure, the heap, the min heap, instead of requiring a union find data structure, which is kind of interesting. But both of them actually have the same runtime complexity.